Let me start with a person, the one you can't call anymore, the one you can't hold anymore. What if I told you they haven't really disappeared? That the you of this moment has simply scanned across to another frame in time? Would you believe me? Don't shake your head just yet. This time I want to use a real physics experiment to talk with you, seriously, about one question. Does time really exist? 24,000 atoms, just 1 billionth of a degree above absolute zero, lighter than dust, lighter than a breath, barely even a thing in an underground lab in Birmingham, England, Professor Barentini pressed a button. He was about to do something that had puzzled physics for 60 years inside a mini-universe smaller than a grain of sand, to summon time out of nothing. It sounds like science fiction, but it's real. On June 11, 2026, the work appeared in Physical Review Research. 71 years earlier, on March 21st, 1955, in Princeton, a man of 76 picked up his pen and wrote a single line to a family that had just lost one of their own. The distinction between past, present, and future is only a stubbornly persistent illusion. 4 weeks later, he was gone too. His name was Albert Einstein. Many people read that line as a dying man's spiritual last words, but Einstein was never moved by the idea of an afterlife. What he meant was his own physics. According to the relativity he built with his own hands, time is not a separate river flowing forward on its own. It's one dimension inside the four-dimensional structure we call space-time, exactly as much a dimension as length, width, and height. So the past hasn't vanished the way we imagine. It's still there in space-time, just not on the slice we happen to be living through right now. You might think this is all abstract chalkboard talk, but the fact that time isn't the same for everyone, someone measured that with real people in real life. Two twins, Mark and Scott Kelly, both American astronauts. Mark was born 6 minutes before his brother. Later, Scott went up to the International Space Station and circled the Earth for 340 days while his brother stayed on the ground. When he came back down and they ran the numbers again, the age gap between the two brothers had gone from 6 minutes to 6 minutes and 5 milliseconds. Flying fast and high, Scott's time really did run just a touch slower, 5 milliseconds of youth gained out of thin air. So up in the sky, there's no single great clock hanging in the middle, keeping time for everyone. There's a line of English poetry that puts it well: everyone has their own time zone. Our own old sayings, in fact, said this long ago: each destiny has its own season. Some rise young, some bloom late. That's not to say fortune-telling can read your fate, but that people thousands of years ago, with nothing but their own eyes, faintly sensed the same thing. Time has never treated everyone alike. The 5 milliseconds the Kelly brothers picked up are still just small change here on Earth. To see how far time can really be stretched, you have to go somewhere far more extreme, right next to a black hole. There's a movie where, long after it ended, a lot of people were still sitting in their seats, not moving. It's called Interstellar. In the film, Cooper and his crew land on a planet that's all ocean, finish their task, and return to the ship. For them, only a few hours have passed, but for the crewmate who stayed behind, 23 years have gone by. Cooper sits down and watches the backlog of video messages. On screen, his son grows from a boy to a father, marries, has a child, again and again saying, "I hope you can still see this," and then stops recording. The last message is his daughter, and she has grown to be exactly as old as the father watching from the other side of the screen. You might think the screenwriter made this up to tug at your heart. He didn't. The person who worked out the time for that planet was Nobel laureate in physics Kip Thorne, who used general relativity to calculate, step by step, how much slower time should run beside that black hole. The planet is so close, the gravity so strong, that time is dragged almost to a standstill. 1 hour there is worth 7 years outside. And by now, relativity's knack for slowing time has shown its two faces. The 5 milliseconds the Kelly twins gained came from speed. Scott was circling the Earth so fast, that's special relativity. The 23 years Cooper paid came from gravity, the black hole beneath him pulling so hard. That's general relativity, and it even has a name of its own: gravitational time dilation. Speed or gravity, either road can force time to slow. And none of this is sci-fi exaggeration. Your phone's navigation can pin you down to within a few meters precisely because the satellites overhead correct every single day for the tiny time difference this bit of gravity causes. Without that correction, it would drift off by more than 10 kilometers in a single day. So a day in heaven, a year on Earth turns out not to be a myth. And Cooper, in the end, falling into that black hole, into a place where every moment is spread open at once, that scene we'll save for last. Let's set aside the big cosmic words for a moment and talk about something you've lived through yourself. On some summer afternoon in childhood, you lay on a cool mat watching the flecks of light between the leaves. And that one afternoon felt as long as a whole childhood. And now a year goes by in a blink. On some night when you fell head over heels in love, the whole city seemed to come to a stop. But in the 15 minutes you spent waiting for your number at the dentist's, time barely moved at all. Why isn't time, for you, running at a steady pace? Physics, over the last 100 years, has been forced toward an answer that isn't very comfortable. The flowing of time may not be a property of the universe at all, but a property of you. It's not the universe that's flowing, it's you who are feeling it. It's you scanning something that was already laid out. Speaking of scanning, remember one word. When you watch an animation, it's really just a lot of still pictures played fast enough to fool your eyes. One still picture is called a frame. A film shows 24 frames a second, and through the brief lingering of each image in your eye, what's called persistence of vision, your brain stitches them into smooth motion. This continuous, flowing world in front of you was, all along, pieced together one frame at a time. In 1967, in Princeton, a physicist named DeWitt set out to do something big, to merge Einstein's relativity and quantum mechanics into a single equation. When he was done, he wrote down a line so short it was unsettling. That line was later named after him and John Wheeler, the Wheeler-DeWitt equation, one of the core equations of quantum gravity, and it describes the entire universe. What kept physicists up at night wasn't that it was complicated, it was that the equation had no time in it. Almost every equation we learned in high school physics has a t in it, telling you what happens the next second. But the moment you describe the whole universe as a single whole, that t vanishes on its own. Later, the physics community gave this a name, the problem of time. If the most fundamental equation of the universe doesn't even contain time, then why is the watch on your wrist still ticking? Why do you still grow old? This is exactly where this field is at its most mind-bending, and its most fascinating. Over 60 years, physicists' answers slowly converged into a single sentence. Time is not a basic part of the universe, but something that emerges from the inside when all things relate to one another. Here's an analogy. Pull out a single water molecule on its own, and it has no temperature to speak of. But when countless molecules are crammed together, colliding endlessly, temperature emerges. Time is like that too. You can even picture the whole universe as a single still painting, with every moment laid out equally across it. And you and I are not outside the painting, we're part of it, entangled with everything else. When you glance back at your watch and feel another second has passed, it's this relating itself that lets you taste change. But to be clear, this relating lets you taste that there is change. Yet which direction that change runs, why it always flows from past to future, and not the other way around, that's a different question. And the answer is hidden in entropy. The Italian physicist Rovelli has a line, "The world is not a collection of things, but of events." In 1994, he and the mathematician Kant proposed that the time we feel emerges from the change in entropy. What is entropy? Entropy is disorder. A cup of hot water slowly cooling down. A tidy room turned into a floor strewn with toys by a 3-year-old in minutes. That's entropy increasing. The reason you can tell past from future is precisely that entropy keeps growing. But you might press further. Why does entropy always increase and never decrease? Because our universe, at the moment of the Big Bang, happened to be in an absurdly low, extraordinarily ordered state. And ever since, it has been sliding toward greater disorder. It's exactly this extremely ordered starting point that gives the whole universe a direction that can only run forward and never back, like a one-way street. Past and future are different only because this street runs one way. This is what we call the arrow of time. So can any of this be tested? Here's the key. If time really does grow out of relating, then even a tiny cluster of atoms, as long as you let them relate to one another and make a little entropy, should grow its own time inside. What physicists wanted was exactly this, a scaled-down model of the universe they could set on a table and observe over and over. In a moment, you'll hear a scary term, Bose-Einstein condensate. Don't be afraid, it's just a cloud of atoms cooled until they're of one mind, all moving in perfect step. This idea stayed on physicists' chalkboards for a long time, until June 2026, when Barantini in Birmingham made it real with 24,000 rubidium atoms. First, he cooled the atoms to near absolute zero, cold enough that they lose their I am me identity and crowd into a cloud sharing a single quantum state. This state is called a Bose-Einstein condensate, something Einstein and Bose predicted 100 years ago. Then, using lasers, he carved a partition 8 micrometers wide right through the middle of the cloud, 10 times thinner than a human hair, splitting this mini-universe in two. The side that's constantly recorded is the bright region. The side left unwatched is the dark region. When the partition is tuned to just the right height, the atoms begin to pour periodically from the dark region into the bright region, and then flow back matter in the bright region, coming from nothing and returning to to nothing. One tiny big bang and big crunch after another, like the breathing of a universe. And to measure time, Barantini deliberately did not use the clock on the wall, he used entropy. When entropy accumulates, time moves forward. When entropy stops changing, time stands still. Let's be clear about one thing first. This experiment did not create or destroy time. Not a single atom was lost, and energy was conserved. What it really achieved was, for the first time in a lab, to use a system's own entropy as a ruler and measure out a stretch of time that belonged to it alone, one that nobody imposed from outside. The result makes you go quiet. When the atoms shuttle freely between the two sides, and each round of entropy is nearly reversible, the clock on the lab wall ticks on as usual. Yet the time inside this cluster of atoms has barely moved at all. Raise the partition to a critical value, and it enters a stable state called heat death, where entropy no longer changes, and its inner time stops completely. Here's something to keep in mind. Earlier, the Kelly brothers flying up in space, Cooper beside the black hole, those clocks in relativity, however much they speed up or slow down, are all still ticking. But this Birmingham experiment goes one step further. When nothing changes anymore, time doesn't run slowly, there simply is no next moment at all. So you might immediately ask, time inside it has stopped, but we stood outside watching for half an hour, and the watch clearly showed half an hour had passed. Isn't that a contradiction? It isn't. This cluster of atoms clock measures its own entropy. When entropy stops changing, it has no next moment, while our watch measures our own changing. The two clocks are simply not the same one. It's like pressing pause on a movie. Everything in the frame freezes. There's no next frame. But the clock outside the theater doesn't stop for a second. The time in the frame stops not because anyone froze it, but because inside it, nothing is changing anymore. And the stopping of time inside that cluster of atoms in Birmingham means exactly the same thing. What Barantini actually measured was just this. The more tightly you seal off this cluster of atoms, the more slowly its inner time runs, until it stops. Yet on the lab's clock, the durations of these processes are identical. That doubt on the chalkboard 60 years ago was, just like that, sealed inside an 8-micrometer glass jar. By now, a bold thought may already be forming in your mind. If time is just entropy increasing, then if I lock myself in a room that's absolutely sealed, cut off from the world, can't I make time stop and live forever? It's a seductive thought, but sadly, it doesn't work. Because you yourself are an entropy-making machine that can never switch off as long as you're alive. Your heartbeat, your dividing cells, even every thought you're having right now are all producing entropy without pause. The physicist Schrödinger had a famous line, "Life feeds on negative entropy." You have to keep eating low-entropy food and oxygen and expelling high-entropy waste heat just to barely maintain that extraordinary, highly ordered state we call being alive. So what about freezing entropy entirely? The only way is to lower the temperature to near absolute zero, minus 273 degrees, pressing the atom's thermal motion to its limit so it can no longer exchange a shred of entropy. But physics tells us that absolute zero itself can only ever be approached, never truly reached. And even if you got that far, every life process in your body would freeze forever at that same instant. That's not immortality, that's death, utterly frozen. So here's where time is most merciless. You can't dodge it by hiding yourself away. Because as long as you're alive, you are entropy increase itself. Speaking of running time backward, you're probably thinking of another movie Nolan again, this time Tenet. On screen, bullets don't fire out, they fly backward into the gun. People walk backward, rain falls up toward the sky. Nolan gave this idea a name, inversion. He didn't just make it up out of thin air, what he grabbed onto is exactly the thread we've been following. Which way time runs depends on which way entropy changes. You can tell before from after only because entropy has been increasing all along. So in theory, run the entropy of a process backward, and time looks like it's running backward too. Barantini's glass jar presses pause on entropy. Tenet presses rewind on the same thread. The film adds one more line that really keeps you up at night. If you truly could move backward through time, could you go back to the past and change something that already happened? Say, make it so your own grandparents never met. But if you did, then who was it that went back to change it? Let's leave that question here for now. We'll circle back to it at the very end. But there's half a sentence I have to nail down first. Whether bullets can really fly backward is, for now, only the movie's imagination. The only part that can be tested by experiment is this. The direction of entropy defines the direction of time. Half of it is real physics, half of it is Nolan's poetry. Enjoy the ride, but don't mistake those two halves for the same thing. If time is emergent, then what's the smallest unit it emerges in? Physics has a number called the Planck time, roughly a decimal point followed by 43 zeros. Anything shorter than that, and our physics stops making sense. In other words, the universe's time may not flow infinitely smoothly, but jump forward frame by frame, like an animation. Mainstream directions like loop quantum gravity and more fringe attempts like the Wolfram Physics Project are all seriously discussing the possibility that space-time is discrete. And Professor Seth Lloyd at MIT, in his 2006 book Programming the Universe, worked out something else that sends a chill down your spine if you treat the whole observable universe as one giant computer. From the Big Bang until now, how many steps could it have computed at most? His answer, about 1 followed by 120 zeros of the most basic operations, and that number is pinned down together by its energy, the age of the universe, and that smallest Planck constant. The speed of light, meanwhile, sets how much information this universe computer can store at most. Some people have also tossed out a popular analogy. Treat the speed of light as the universe's CPU clock speed, and the Planck time as the universe's frame rate. But here I have to stop and give you a word of caution. Space-time may be discrete at the deepest level is a physics hypothesis that can be tested by experiment. The universe is a computer is a philosophical interpretation that cannot be tested. We live in the Matrix is the Hollywood simplified version. These three are not the same kind of thing at all, and they get stewed together all the time. This boundary is one you have to keep clear in your mind. Now let's leave the modern lab and go back 1,600 years to the year 402 in Chang'an. A great monk who had crossed snow-capped mountains and walked across deserts from the western regions, Kumarajiva, presided over a vast translation hall in Chang'an and produced a short scripture, its whole text barely more than 5,000 characters, the one that would later be called the Diamond Sutra. From beginning to end, it asks only one thing, that appearance your eyes and ears catch, and your mind works up what is it in essence. Its most famous line comes in the 18th chapter. The mind of the past cannot be grasped, the mind of the present cannot be grasped, the mind of the future cannot be grasped. One of the most rigorous modern scholars of Buddhism, Master Yin Shun, explains it almost cruelly. The mind of the past is already past, and if you try to grasp it, you can't. The mind of the future has not yet come, and if you try to grasp it, you can't either. And the mind of the present is changing, flowing away right now, and if you try to grasp it, you still can't. It's like trying to take a photo of a river. The water of a second ago has already flowed downstream. The water of a second from now hasn't arrived yet. And this present second, in the instant you press the shutter, has already become the past. The Diamond Sutra takes the road of sitting still, of looking inward, of seeing with one's own eyes, a road completely different from Einstein's, from that equation, from that experiment in Birmingham. And yet, strangely, what they glimpse seems to be the same direction. Even more striking, Rovelli himself, in his 2020 book Helgoland, set aside a whole chapter to discuss the 2nd century Nagarjuna's Mula Madhyamaka Karika. He said Nagarjuna's emptiness, that nothing has an independent, self-determining existence, but is only a node within relationships, echoes his own relational quantum mechanics in a way he can't ignore. He's not painting mysticism onto quantum mechanics. This is an echo acknowledged, in his own words, by a physicist rigorous to the point of harshness. Let's lay them all out on one table. On the physics side, the Wheeler-DeWitt equation has no time in it. Kahns and Rovelli say time emerges from entropy. Relational quantum mechanics says a physical quantity has no value of its own, plus Barantini's experiment and the letter Einstein wrote to Besso's family. On the side of the Eastern texts, the Diamond Sutras, none of the three minds can be grasped. Yogacaras claim that time is a label the mind attaches to the world. Nagarjuna's all things are relationships. 8 clues, 4 methods, mathematics, experiment, first-person introspection, philosophical arguments spanning about 1,900 years, all looking toward the same direction. Time is not something the universe had to begin with. It emerges from deeper-lying relationships, and is then worked up by your consciousness into a feeling of flow. This is nobody's victory. The Buddha did not foresee quantum mechanics long ago, and Rovelli did not prove Buddhism with physics. The two went their own separate ways and happened to meet at a certain point, and that fact alone is worth going quiet for and taking seriously. But here I have to add one honest note so you don't drift off course. There's no time at the deepest level of the universe, and the time you live your days by is fake, or two completely different things. There's no time inside that 8 micrometer glass jar, but you're rushing to catch a train, you're waiting for someone, you're getting through one miserable long night. That time is constructed for you by your brain, real and solid, and for your life it is 100% real. Blurring these two things into one is exactly the cheapest and most dangerous, slippery slope of this kind of topic. And there's an even more baffling layer in quantum physics. Things like electrons, like light, when no detector is watching which path they take, behave like a wave, interfering and superposing with themselves. But the moment you set up a detector to observe, that wave snaps, collapsing into individual particles, and the interference pattern vanishes in an instant. It's the act of observing itself that changes how it shows up. And here I have to nail one thing down. The observation quantum mechanics talks about means any physical interaction whatsoever. A detector, a barrier, even a single photon hitting it, all count. It has nothing to do with whether there's consciousness or whether anyone is watching. So the observer I talk about below is always a frame of reference in the physical sense, not a thinking soul. Rovelli follows this road to the end and proposes relational quantum mechanics. A thing's properties have no value that it alone decides, only values that exist relative to some observer. This has the same flavor as what Buddhism means when it says the seeing and the seen were never separable to begin with. But I have to say this flatly. This is not, you can change the world just by having a thought. That's the nonsense of stewing science and Buddhism into one pot. It only says the observer was never someone standing outside the world, watching coldly from afar. So that you, the one who can see, who can be present, who can love, is never inside any single picture. It is the one who has been watching all along. After all of this, I'm not trying to convince you that time doesn't exist. I only want to ask you, the next time you're being dragged along by a deadline, by anxiety about the future, by regret over the past, try the simplest thing. Ask yourself one question this frame. Right now, is it imposed on me by the universe, or did my consciousness just happen to scan across it and call it now? Don't rush to find the answer. The instant you stop and ask, you're already no longer someone being pushed along by time. Back to 1955, Princeton. When Einstein wrote that letter, he was using his own relativity to earnestly comfort the family of his dear friend Besso, the old friend who had gone a step ahead of him. His relativity tells us, time and space were one all along, a single four-dimensional spacetime. Remember that bullet in Tenet, flying backward into the gun? Well, even if entropy really could be run backward, even if you really could move backward through time, the past that can't be changed in that film still can't be changed. Why? The answer, Einstein had already written in this letter. The past is not something that has vanished. It can't be changed, not because it's too far away, but because it has always been there. Later, someone followed this conclusion and made an analogy that spread far and wide. Set a cup on the table, three-dimensional, with length, width, and height. Sunlight slants in. The cup casts a shadow on the tabletop. The shadow is two-dimensional. It moves, it deforms, and it has its own now. But the cup itself stands there, whole, the entire time. The shadow's whole history, how it looked in the morning, at noon, at dusk, is really all there in the cup, existing all at once. This analogy says, we, perhaps, are that shadow. Your whole life, birth, childhood, this moment, your eventual death is already laid out, complete, on that four-dimensional you. The reason you feel now is moving and the past is vanishing is only that your consciousness can sweep across just one frame at a time. Whichever frame you scan to, that's the one you call now. At the end of Interstellar, Cooper falls into the black hole and lands in a strange place. Every moment of his daughter's room laid out before him at once, layer upon layer, so that a reach of the hand can touch any frame. That is exactly this four-dimensional cup turned into a picture. As for sending words back to the past through love, that's the movie's poetry, not physics. But the reason it brought tears to so many eyes is that it turned this most abstract idea into something concrete. A father who, across time, can still reach every frame of his daughter. If everything up to here is true, then, just as Einstein told Besso's family back then, Besso has not truly vanished. He is simply not on the frame your consciousness is scanning right now. And the one you thought had left forever, the one you can't call anymore, the one you can't hold anymore perhaps, the same is true of them. They may still be there, still in the frame where you two laughed till it hurt, still in the frame where a reach of your hand can hold them, still in the frame where they're alive and well, talking with you. Those frames never disappeared. It's not them that vanished, it's you. It's the you of this moment, who has already scanned across to another frame in time. If you're willing, leave a little room in your heart for this possibility. Maybe you'll feel a little better. And if this video made you think of someone too, then sit with them a while longer, in your heart. And the person right beside you now, this frame of theirs will also become, someday in the future, a frame you'll miss. Don't keep gazing at the frames already gone, and don't only long for the frame that hasn't come. The only thing you truly hold is this frame, the one you're scanning now.